Okay, are we live? Okay. I don't know what keeps happening. Something keeps disconnecting, and then when I try to like fix it, it just like crashes my entire computer. Okay, and I don't like the lighting here. All right, so let's start to figure this out. This that improved it a little bit. Okay. All right. So wait. First off, we should probably just have that is not gonna work. You need I need like something to hold this thing. Okay, so the SIR model is SIR. We have S dot is equal to minus alpha S times I. Then we have I dot equal to alpha SI minus beta I. And then R dot is equal to beta I. So that's the whole SIR model, just 3 equations. Now, problem 1 says, for the SIR model, show, okay, so 1, show S plus I plus R is equal to 1. Directly. Okay. Okay, so they had this in the I gotta wake up, man. So the question is, how do you use these differential equations to know? All right. Bruh. I'm gonna cheat on this one. I don't even know how you do that. There's a hint in here that says let's see, there's a hint. Oh. Okay, wait. All right, that's enough for me. We can figure that out. Okay, all right, that makes sense. So, um, so what we want to know is that let's let n of t is the number of people equal s plus I plus r. Okay, then take dn of t dt equal to minus alpha si plus alpha si plus minus beta I plus beta I. So these cancel, these cancel. So therefore, dn of t dt is equal to 0. So then, therefore, the population is never going to change in this model. All right. So that doesn't exactly show that the population is 1. But if you start with an initial total population of 1, then it's going to stay at 1 for all time. All right. Problem. Let's do problem. Okay, problem 2 says, in the SIR model, we assume everyone in the population is susceptible at time t equal to 0, except for a very small fraction that's already infected. Suppose that some fraction of the population has received a vaccine so they cannot catch the disease. The vaccine makes the fraction of the population that is susceptible smaller. Okay, then it says use a solver, numerical integrator, and solve the system for a bunch of different parameters. All right, let's do problem 3. So problem 3 says, vaccines make it possible to prevent epidemics. However, the time it takes to develop a vaccine may make it impossible to vaccinate everyone in a population before a disease arrives. For the SIR model, which initial conditions guarantee... Okay, so which initial conditions guarantee that di dt is less than 0? Okay, so what we want is which initial conditions give I dot less than 0. Okay, and it says your answer should be written as A in terms of A and or alpha and beta. All right, so okay, so what we need is that beta I is greater than alpha SI. So that means that beta is greater than alpha S. So then S is less than beta over alpha. That's my solution there. Okay, then part B says for given values of alpha and beta, what fraction of a population must be vaccinated before a disease arrives in order to prevent an epidemic? Which fraction um um hmm. Right, so if those infected people recover faster than more people can get infected, then it's just going to go to 0 before the susceptible actually grows. But now the question is, how do we? I don't even know what it means for when they say for given values of alpha and beta, what fraction of a population must be vaccinated before a disease arrives? So if is it not just beta over alpha? So okay, so let's say that like 10% got vaccinated. That means that the susceptible population, we're actually removing the susceptible from the population of our model because they just can't get infected. All right, let's look at the answer. So I got the first one. The first one is just like figure out how to make the derivative of infected less than 0. But now, how to I guess what you could say is you could say you want to remove enough susceptible such that beta is such that alpha times s is less than beta. Okay, all right, I get it. So what we need to do is let's say V is the proportion of vaccinated. Then 1 minus V is equal to S, right? So then what we want is we have 1 minus V is less than beta over alpha. Okay, so then we can just do some algebra and we get V is greater than 1 minus beta over alpha. All right, so you need the vaccinated population to be greater than 1 minus beta over alpha. Okay. Can we just go through the integration? Let's go through the integration. Okay, so what we want to do is we want to find the expression of I of S. So we have di ds, and if we integrate this, then we get I of S. And this is going to be equal to di dt times dt over ds. So this is going to be equal to alpha si minus beta I times 1 over minus alpha si. Okay, so then this becomes 1, so this becomes minus 1. Then this becomes plus alpha beta s. Wait. No. What am I talking about? This becomes plus beta over alpha times 1 over s. The i's cancel. So this is equal to di ds. Now we can integrate both sides, and we get minus s plus beta over alpha ln s plus c. All right, so that's the integration. So this is I of s. This is kind of interesting. I've never really seen this method before. So you solve in terms of another dependent variable. All right, so but that whole thing is pretty straightforward. But I haven't done a maximization problem in a long time. So the problem is we have I of s is equal to minus s Okay, so the problem is Determine the maximum value in terms of. Okay, wait. Okay, so that equation is under the assumption that S of 0 is equal to 1 and I of 0 is equal to 0, approximately. Okay, this is fun. Okay, so this is with S of 0 equal to approximately equal to 1 and I of 0 approximately equal to 0. And then we have let rho equal beta over alpha, find I max in terms of rho. So this becomes I of S is equal to minus S. This is plus um, okay, so if we take the derivative of this, ddp, we get this is going to be 0, and this is going to be ln s. So then don't we want to then find the zeros of this? So the zeros, so it's gonna be rho equal to 1 because ln of 1 is equal to 0. So this is what we want. So the maximum is going to be when. Okay. I'm pretty sure that's true. Okay, let's just check our answer then. On 2.7. Oh, they don't have 4. All right, we need to ask Chat GPT, bro. Oh wait, there's a part B though. Okay, so the part B is the statement the epidemic cannot get started if beta is greater than alpha. True or false? Okay, so part B is if beta is greater than alpha. If beta is greater than alpha, then this is greater than 1. And dude, there's something about being inside in a cave that's just so annoying being in a cave. All right. Oh, I did 4 wrong. 4 is wrong. Okay. Yeah, 4. I think you need to take the derivative with respect to s. No, wait, no, that doesn't make sense because then you just get back the original differential equation, right? Which is -1 -1 plus rho. Oh. Oh, wow. I'm so off my game right now, man. I don't know what it is. Okay, this is all wrong. This is all wrong. Okay, so what you need to do is, because the dependent variable is s, so if you take di of s ds, you get -1 plus rho over s, because the derivative of ln of s is 1 over s. And then you set this equal to 0 to find the critical points. Then you get p is equal to s. Okay, then if you plug that in, you're going to get minus s plus s ln s plus 1, which is equal to minus, but you want to write it in terms of rho. So what you're going to be doing is you're going to be calculating I of rho is equal to minus rho plus rho ln rho plus 1. So this is I max. Okay. Now, what's the second part? Oh, man, this is a tricky section. Okay, that makes sense. All right, so, okay, so with these initial conditions, our equation for I dot becomes I times alpha s minus beta, but this becomes 1, so then we get I of alpha minus beta. So if beta is greater than alpha, then this term is negative. So then I implies that I dot is less than 0. So yeah, so okay, so that makes sense. Okay, let's see, what's the next problem? Okay, so 5 is just a Desmos problem. All right. So problem 5. Graph I of s. Let's just ask this thing to use Python. Okay, 6 seems kind of fun. So if we look at problem 6, we add in a term that so that susceptible can refill. Derive a system in 2 dependent variables, S and O. All right, that's probably pretty good. And we'll skip D. How does the system change if we fix alpha? It shouldn't cross this axis though. And then what is part B? Part B is okay. I don't really understand the graph in B. Oh, so you solve for this and you get S minus 1 over ln of S is equal to rho. Let's see what the code says. Wow, it did like a Newton's method type of thing. What the hell? That's wild. Wow, I can't believe it wrote this code. What's up, guys? Hanzi and Game Master. Guys, I'm not locked in right now, so it's nice to have some hype. All right, so let's do number 6. I think I can do number 6. Number 6 seems doable. All right, so let's switch over. I'm not shirtless right now. It's not warm enough. All right. So we're modifying the SIR model to have a gamma. I can never write my gammas right. Gamma R. And then this is going to be minus gamma R. Okay, so we want to show part A is show that S plus I plus R is still equal to 1. So we assume that the initial condition does sum to 1, but now we just take d dt of S plus I plus R, and we're going to get the same thing we did before, but I'll do it again. We get, just sum these three things. So we're going to get minus alpha Si plus gamma. I'm just going to use my thing, gamma R, plus alpha Si minus beta I, plus beta I minus gamma R. So then this cancels, this cancels, this cancels, this cancels, this cancels, this goes. Therefore, if we let equal to n of t the sum of the states, then dn dt is equal to 0. So therefore, it's a constant. Okay, now part B is derive a system derive the system in terms of I and S. Well, that's no. I mean, you don't end up taking any derivative because your differential equation is all you have. I mean, you don't even have expressions for S, I, and R. So by doing this, you're just referring to the differential equation system. So you're not actually taking any derivative. The point is just to show that this sum is equal to 0. Okay, so by letting R equal to 1 minus S plus I. So if R is equal to this, then we should be able to take d dt of 1 minus S plus I, which is going to be equal to 0 plus alpha Si. Wait, this is a 1 minus this. So we're going to minus alpha Si plus beta I. And then finally, and then I guess for this, we also have, what is this? This is going to be minus gamma R, which is going to be minus gamma of 1 minus S plus I, right? So we have to replace it. So that gives us, so what cancels? This cancels, and then this could be minus is this minus though? It's minus, right? So we have this plus beta I. And we can see that this is correct. This is correct because you just take that. Okay, but now, so, but we need to write the whole system in terms of that. So that's just a matter of replacing the R. Okay, so we're just going to get S dot is equal to minus alpha Si plus gamma 1 minus S plus I. And then I dot becomes alpha Si minus beta I. This doesn't change. So this is the new system. All right. So that's deriving the system in terms of two variables. What are the equilibrium points for this model of the two variables? Okay, so we now need to solve this equal to 0. All right, so we have minus alpha Si plus gamma minus gamma S minus gamma I, okay, is equal to 0. And we're trying to find the equilibrium points, so we're trying to find the values of the states. And then we have 0 is equal to alpha Si minus, okay, so I equal to 0. So if I is 0, then gamma times 1 minus S must be 0. So we can just do this. Which means gamma minus gamma S is equal to this. So S equals 1. So oh yeah, right. This is always going to be the case where there's no infected people and there's, okay, and then everyone's susceptible and nothing happens. But let's not assume that I mean, I'm sure we'll find, but interestingly, 0 is not an equilibrium because, well, the infected doesn't change. We have this base growth on, we have this base growth on the susceptible population, which so I know that we have that equilibrium point, but that equilibrium point's, I think, the boring one, right? But okay, so let's just say that S is equal to beta over alpha. Because then if you have alpha S is equal to beta, then that goes to 0. So now we can plug that in. So we get minus alpha times beta over alpha I plus gamma or minus gamma. Jeez. Plus gamma minus gamma beta over alpha minus gamma I. So this cancels out. You get minus beta I plus gamma. Well, let's just do this. 1 minus beta over alpha minus I. I mean, you also get, so if I is equal to 0, if I is equal to 0, this goes to 0, this goes to 0. Wait, what? How did that happen? Oh, because this is not right. That's not going to be the case. Yeah. All right, let's do it differently. Let's do it. So, so say I times beta plus gamma is equal to gamma minus gamma, or let's just do this. So I times beta plus gamma is equal to gamma times 1 minus beta over alpha. So then we just divide, right? So I gamma, oh wait, this is gamma 1 minus beta over alpha divided by beta plus gamma. All right, I think that is the fixed points, but we'll double check. But I'm pretty sure that is right. So let's just all right, so part A was easy. This becomes, yeah, you just plug in for that. That's easy. Then equilibria, you get, yeah, so there's that one. That was easy. Yeah, so I equal to 0. Wait, but then if, oh, okay, I see what they're doing. Okay, so if I is equal to 0, then we get s equal to 1. That's the simple case. Now, if s is equal to beta over alpha, wait, did I switch over? Yeah, I did. Okay. Then you set ds dt equal to 0, and you get gamma times 1 minus beta over alpha. Yes, all right, good. We did it. So we did get that one right, which was nice. Do I do tuition? What is that? What is the picture on the bottom right? Bottom left? It's just like a random little picture. It's supposed to be me teaching math. Oh no, I don't do tutoring. I don't think I don't think I'd be a very good tutor. Maybe. All right. I just like streaming. If I were to tutor, man, I would stream all the tutoring. All right. All right, let's do what? What? Okay, wait, hold on. This. All right, so problem 7. Here, we'll read it. I'll just write it down. In the movie I Am Legend, infecteds work together to increase the number of infecteds. We can modify the SIR model to include the assumption that zombies actively infect susceptibles by replacing I by square root of I in the interaction term. Okay, note that I is between 0 and 1, so square root of I is greater than I. We obtain the system. All right, so let's do that. So instead, so I'm going to leave this up, but this is not the system. So we get, 1 Okay, we get s dot equal to minus alpha s square root I, and then I dot is equal to as square root of I minus beta I. I'm just gonna make them a and b. It's like why go to Greek? Calculate the equilibrium points. Okay, so a is fixed points. All right, so we just set this to 0, set this to 0. So clearly, 0, 0 is one of them. But we can also take square root of I as minus b square root of I. All right, so if we did as minus b square root I equal to 0, we get then s dot is equal to minus a minus beta square root I over a. These cancel, and then this is square root of I. So then we get beta I equal to 0. So I think we get I equal to 0 here. So these are our two solutions. So what are these streams? Are you streaming progress? Yeah, just progress. I'm in school and it's like I might as well record them. Okay, I'll be back in a minute. All right. Biology, bro. All right. Find the region of the phase plane where di dt is greater than 0. Okay, so B. Wait, we need to switch. Okay. All right, so wait, let's write these. A is 0, 0, and b square root of I over a and 0. erase this. And so part B is find I greater than 0. So where is... I was computer science for a while, so I like math, but I want to apply it. Where's my iPad? So let's just read this problem. Find the region of the phase plane where I dot is greater than 0. So the phase plane is going to look like this. We're going to have S, and we're going to have I. Now, okay, so we have the equality AS squared root of I is going to be greater than BI. Okay, so we should get AS is greater than B square root I, right? Wait, is that right? If we have, this is going to be 1 over square root of I is equal to I minus 1/2. Yeah, so that's right. So then S is equal to, we're going to say equal because we're just going to plot a graph. So this is going to be B over A root I, which corresponds to that. So square root of I. Wait, we actually want the other way around. We want so we want I is equal to alpha over beta S squared. So something like this. So but let's keep track of the inequality. So if greater, so if this is less, so if we're in here, then I dot greater than 0. Maths is definitely the best subject. Okay. So I think there are so many books that I want to read. I think I'm going to try to work through. So if I wasn't in this class I really want to work through this book, Nonlinear Dynamics and Chaos. It's one of the great differential equations books in the world. But then I also want to work through this book. It's called Introduction to the Theory of Computation. That book is badass, man. And I've done a few chapters of that. And then I really want to work through this self-study. Here, I'll show you. This is the book. Stipser Theory of Computation. Anyways, it follows this book. So it covers 3 things, basically. It covers what is computation and what are the different models of computation? What are the limits of computability? What is computable? And then finally, what is efficiently computable? Meaning, what can we really do with computers in a reasonable amount of time? And it's dope. And I have the book. And then I want to also read this abstract algebra book. Okay, wait. So let's just make sure that we got this right. So the equilibria. I did not get that right. So s dot equal to 0 means implies I is equal to 0 or if I is equal to alpha squared over beta squared times s squared. Yeah, if I is equal to that, right, I guess I should have noticed that. I didn't really notice that. So if I is 0, no matter what, then this system is at equilibrium. If I is greater than 0, oh wow. Okay, so I did not do that right. All right. But I did do this right. If I is less than alpha over beta s all squared, yeah, so that, and then, so, I think I have a stream going through some of that stuff. And then there's this online, well, and I really want to do real analysis. So I've always hated analysis. Yes, I agree, Raman. I've always wanted to do real analysis, but I've always sucked at it. I just don't really like analysis. Yeah. So okay, so the book that I'm gonna work through is Understanding Analysis. This one seems pretty good. It's pretty short, um, but it is cool. I mean, delta, like epsilon delta proofs aren't that hard, but it's just like, I don't know. I hate like inequality proofs and stuff like that. Oh, nice. Well, good job, man. And then and then let's see, what other books did I want to do? Yeah, okay, I guess there's this one. This is the abstract algebra one. Marco Hein Abstract Algebra. This book I think I'm gonna do this one. Get into some Galois theory, stuff like that. I've always been more of an algebra guy than wow, you should definitely take an abstract algebra class. I mean, if you're probably gonna have to take linear algebra, and once you realize, like, I don't know, the vector space, like a vector space has a group embedded in it and stuff like that. Like, I would say abstract algebra is the study of like common mathematical structures. Linear algebra is very useful. Linear algebra is like probably the most useful directly, just because it comes up so often. But um, let's see, what's the definition of abstract algebra? Let's see how Wikipedia defines it. Abstract algebra is the study of algebraic structures, which are sets with specific operations acting on their elements. Yeah, it's really just like exploring the space of possible mathematical structures. But it's pretty fun. Could you take a look in my modules in my course? What does that mean? Whoa! You did a linear algebra class. You barely touch on vector spaces. How is that even possible, man? No, but I kind of agree with you because the. Could you take a look in your course? You'd have to give me a link or something. But yeah, vector spaces are like the main object of study. But I agree with you. My linear algebra class right now, it's basically for the first like 4 weeks, it was all just doing matrix addition and row reduction and stuff like that. It might not let you send links. I don't know. Some YouTube's kind of weird about that kind of thing. Let me see if it shows up on my phone. I don't typically open up links on stream. Not working. You could send it in my Discord if you want. Okay, let's read the next problem while that's happening. I kind of want to just get into the review exercises. Let's skip 8. Well, I think 8 we have to do. Many zombie movies are based on the premise that zombies do not stop infecting new victims until they're destroyed by a susceptible. In addition, the susceptibles destroy as many zombies as they can. We can model the spread of zombies in such a movie by assuming that the zombies become recovered, i.e., zombies who cannot infect susceptibles. Okay, all right. I'm not going to pull it up on stream, but I'm looking at your thing right now. All right, first year, intro to applied math, calculus, differential equations, linear algebra, statistical modeling, analysis. Okay, second year, computational science, classical mechanics, calculus of several variables, introduction to probability, vector calculus. Okay, third year, I don't even know what advanced computational science really means. I don't know what that course covers. Advanced mathematical methods, complex analysis, PDEs. That's pretty cool. I'd love to take a PDE class. And complex analysis. Complex analysis seems crazy, man. All the pictures of all those analytic functions are so beautiful. Ooh, mathematical biology. That sounds cool. Metric spaces. I want to take a class like that. Numerical methods, dynamical systems, and then fourth year, complex networks. That's cool. Machine learning, general relativity. That's kind of a weird one. And then fluid dynamics. That's pretty fun. That seems like a good course. What do you think you should do on the side? I don't know, man. For me, if there's a class that teaches like the halting problem or like Gödel's incompleteness theorem, something in like logic, because I don't know, for me, I love that kind of stuff. The limits of human understanding. What can we prove? What is provable? But it's not very applied. It's like what do you do with that information? But I don't know. All right, let's get back into it. Okay, so we get this system. Let's write this system down. Hansi, that seems like a good program, though. Is that in Dublin? Are you in Dublin? Dude, that's sick. Bro, if I'm ever in Ireland, I'll hit you up, man. Ireland seems awesome. I've never been to Ireland. I've been to London. I went to London a couple years ago. I'm in California. I'll just leave it at that. I'm not going to answer the actual, but I'll just leave it at I'm in California. Um, um, okay, so let's get back to doing some problems because I have a lot of work to do. All right, so we have a new model. So let's. All right. Okay, so our new model is. All right, so what they say is we can model the spread of zombies and amoeba, assuming infected become recovered who do not infect susceptibles. Wait, this is a weird system. So we get S dot is equal to minus A S I. Then we get I is equal to A S I minus Y S. So the first thing is fixed points. And the second thing is find I dot greater than 0. And then, okay, so this is the same problem as the last one. So, okay, so clearly, if S is 0, so S equal to 0 for all I is fixed. Because if we have a 0 here, then this changes to 0. If we have a 0 here, this is 0. But now, if we get so 0 is equal to S times AI minus Y. If I think it's just this. I think it's the same as the last one. It's like we only have the case where. But now if I is greater for B, if I is greater than Y over A, then if I is greater than Y over A, then I dot is greater than 0. So if we like so there's going to be some so if this is I and this is S, then there's going to be some like there's going to be some line in here such that this is all I dot greater than 0. I'm not actually certain on that. Oh wait, you know what? Wait. Yeah, I think that's right. So this whole region out here. Oh wait. No. This is wrong. This should be. We have some line. This, and this is the value of that. Then this is I dot greater than 0. So I think the fixed points are the same. It's just any time when S is 0. Can we think of anything else? Imagine if S is not 0. If S is not 0, then I has to be 0. But if I is 0, then S has to be 0. So this is all of them. This is the only way. Let's just double check though. Yeah, so the entire line of S. Okay, so we were right about that. I is greater than gamma over. Okay, cool. So we got it. That one was pretty easy. All right, so since this is not on my quiz, I'm probably gonna do this on the weekend. But what we are gonna do is I'm gonna end the stream, and I'm gonna switch over to just review. Well, actually, let's read what's in here. Let's just like skim this. This, I mean, I've read. I mean, this is like the coolest thing ever. But we have seen the behavioral solution of autonomous system can be much more interesting and complicated than solutions single. A plane has much more room, so solutions can do many more interesting things, like periodic solutions. There's still definite restrictions on the type of phase portraits that are possible for autonomous systems. As we learned, the uniqueness theorem implies that solution curves must agree entirely if they intersect at all. For example, if there's a periodic solution that forms a loop in the phase plane, then solutions with initial conditions inside the loop must stay inside for all time. 2 or 3 solutions can fit together to divide the phase plane. And solutions must stay in the same region as their initial condition. Okay. If we raise the number of dependent variables to 3, the situation becomes much more complicated. A solution of an autonomous system with 3 dependent variables is a curve in 3-dimensional space. The uniqueness theorem still applies, so solution curves must either... Yeah, you have a lot more space. Wow, topologically you have way more space. That's kind of crazy. The uniqueness theorem applies, so solution curves either agree completely or do not intersect. But in 3 dimensions, this restriction is not nearly so confining as it is in 2 dimensions. Bro, I never thought about the topology of it. Or I never thought about it in this way. That's so sick. I like this one. The first to realize the possible complications of 3-dimensional systems was Henri Poincaré. Poincaré, while working on the Newtonian 3-body problem from the motion of the planets, realized that systems with 3 dependent variables can have behavior so complicated that he did not even attempt to draw them. Today, we can easily draw numerical approximations of complicated solution curves with a computer. The problem now is to make sense of the pictures. This is an active area of current research in dynamical systems. The complete story for systems with 3 dependent variables is still far from being written. Wait, okay, I shouldn't be doing this on this. Bro, Subham, come on. 8 over x plus. Dude, that's so easy. Isn't that just minus 8 over x squared plus 36x to the third? Something like that. It's really easy. All right. Okay, let's yeah, this is the book I read. Chaos Making a New Science. This book rules. I love this book. Okay, so we did the SIR system. Let's get to these review exercises. Okay, so I'm gonna end and restart. I know, I know, right? Okay, so I'm gonna instantly restart this. I'm just gonna change the name of the stream so that it's all categorized properly.